Right, this is question 10 from the paper one review pack on complex numbers. Um, so we have an Argand diagram, we have this whole thing going on, we have some definitions for what the various complex numbers are, and positive direction are real, so it's greater than A, sweet. Show that the, so the first question asks us to show that if we multiply z1, which is here, by the conjugate of z2, we get that. So let's just see what happens when we do that. Well, z1 is defined as r1e alpha I. z2 is r2e theta I. So the conjugate of z2 is going to be r2e negative theta I. So if I multiply r1e alpha I times r2e negative theta I get r1 times r2 e alpha minus theta I, which is exactly what we were looking to get here. So we've got that, and we're good. Okay, next question. Given that that equals 0, show that that is a right angled triangle. Okay, if that is equal to 0, if the real part is, well, the real part of this complex number is going to be r1 times r2 times the cosine of alpha minus theta, because that's going to be our real part of it. So if r1 times r2 times the cosine of alpha minus theta is 0, that means that the cosine of alpha minus theta is also 0, because if I divide it by r1, r2, I would get that, which means that alpha minus theta has to equal the arc cosine of 0. And the arc cosine of 0 is pi over 2. So that means that the angle in between those two complex numbers is going to be that alpha minus theta is pi over 2, which is 90 degrees. We've got a right triangle. That is very doable. Okay, now we're told to consider the case where it is an equilateral triangle. If we're going to be talking about equilateral triangles, we have to recognize a few rules. All angles need to be pi over 3, which is 60 degrees. And also R1 has to equal R2 because the equilateral, the sides are the same length as well. Don't think that's too hard. We got that. So if I want to write R1e to the alpha I want to write it in terms of R2e to the theta I. So we have to write it in those terms. So let's look at how we might be able to do this. First and foremost, if the angles are that, then alpha minus theta has to be pi over 3, which means that alpha is the same as theta plus pi over 3, right? So already we've got R1e to the theta plus pi over 3 I. We've already stated that R1 and R2 are the same, so that would be R2e theta I times e pi over 3 I. Well, this right here is the definition of that right there. That's z2. So to write this as 1, this is going to be z2 times e to the pi over 3I, and that is the same as z1. Okay, that's doable. Next, we have to show that z1 squared plus z2 squared is z1 times z2. All right, that seems entertaining. So z2 squared equals z1 times z2. All right, so we have to get ourselves there. If I want to try to get rid of, I want to use what we just learned in that last question to kind of simplify things just a little bit here. So if I did that and I wrote this instead as z2 e to the pi over 3I squared plus z2 squared. If I did that, I would get z2 squared e to the 2 pi 3I plus z2 squared. And then this would give me, if I factor out the z2 squared, and I would have e to the 2 pi over 3 plus 1. Right, and now I'm going to turn and work the other side just for a little bit so I can see if I can't make these look the same. So the other side would be z2 e to the pi over 3I times z2. So that's z2 squared e to the pi over 3I. So what my job becomes now is I have to show that this and this are actually the same. So I'm going to switch to modulus form here for this because I think that that's going to be way easier. So if I did that, that would be, well, cosine of 2 pi over 3 plus I sine 2 pi over 3 would be 2 pi over 3, that would be negative 1/2 plus square root of 3 over 2I. And then when I add 1 to that, I would get 1/2 plus root 3 over 2I. Working here, cosine of pi over 3 plus I sine of pi over 3 is 1/2 plus root 3 over 2I. These two are equal, so these are equal to each other. All right, I can dig it. We've done that. Let z1 and z2 be the distinct roots of the equation that. All right. So if those are the distinct roots of that equation, so z squared plus az plus b equals 0. If z1 and z2 are the roots of that, so let's look at the sum of the roots and the product of the roots. I always write this down wrong the first time, but the sum of the roots is negative the second value divided by the first, and the product is negative 1n, the last term divided by the coefficient of the first. All right, so the product of these, or the sum of these roots would be a divided by 1. So if I added z1 plus z2, I would get a. The product of the roots would be the last term divided by the first. So my product of roots, so z1, z2, is just going to be b. All right, with those defined, we can do a little bit of work. We know from earlier that z1 squared plus z2 squared is equal to what is the product of the roots. So right away we can do z1 squared plus z2 squared is the same as b. If I take and I square this, I would get a squared is z1 squared plus 2z1 z2s plus z2 squared. So a little bit of fancy substitution and moving things around. Remember, if I take and I add this and this, I get the product of roots again. And if this we recognize is b, then this would turn into a squared equals 3b, right? So a squared a squared minus 3b is where we get 2. And that has to be 0. So we got ourselves to that one. Sweet googly moogly. Consider the equation that there's only one triangle that can be formed. Okay. So now, moving on, we've got z squared plus az plus 12 equals 0. Well, right away we know that b is 12, and we should be able to figure out that a squared, minus 3 times 12 is 0, so a squared equals 36, so a is either plus or minus 6. That sets up two different equations. The first equation is z squared minus 6 z's plus 12 is 0. The second one is z squared plus 6z plus 12 equals 0. That doesn't factor. I can't think of two numbers. Multiply. No, that doesn't factor. So we have to use quadratic formula. So 6 plus or minus the square root of 36 minus 48 all over 2. So that's 6 plus or minus the square root of 12 over 2. 6 plus or minus 2 square roots of 3 all over 2. Oh, that's 12i. Simplifying that, I would get 3 plus or minus the square root of 3i. And if I did the same with this one, it would just turn into negative 3 plus or minus the square root of 3i. So those are the two possible solutions where z1 is, because z1 is the Z1 has to be the bigger one. So looking at where these would be in space very quickly. So if I'm on an Argand diagram, -3, -√3, I'm working with this one here, and -3, +√3 would be that one there. If I look at this one here, I would have 3 and then up 3 and 3 and then down 3. Okay, just so we have that. So if I use this one, so my Z1 has to be there because it has to be bigger than Z2. My Z2 would be there. So the argument of that'd be -√3 over 3 is going to be the arctan of √3 over 3, which would be pi over 6. But we're in the third quadrant, so it's actually going to be 7 pi over 6. Similarly, the arctan of this one here would be -3, which would give me 5 pi over 6, because that would be here. So if I did that and I did 7 pi over 6 minus 5 pi over 6, I would get 2 pi over 6, which that is pi over 3. So that one definitely works and makes an equilateral triangle. It's my assumption that this one will not. So this is it's my larger angle. So this one is my Z1, this is my Z2. If I was going to do that, I would get the arctan of √3 over 3, which is pi over 6, and the arctan of -√3 over 3, which would be 11 pi over 6. And if I took and I subtracted 11 pi over 6 minus pi over 6, I get 10 pi over 6, which is the same as 5 pi over 3. And that is outside the bounds of my domain, because I can only go here. So there's only one equilateral triangle that works. And the elementary kids are coming in, and it's really loud, so I'm going to stop.